started. So what we're going to be talking about today is essentially PFRs, starting with adiabatic systems. So we've touched on that, and it was in the homework. But we'll go over a little bit more of that, and then we're going to move towards reactors with combined heat exchange. Okay, we'll talk about how to set up the differential equations to solve those, and then I'll pull up on Excel a couple of spreadsheets where we've already done the same method that I showed you earlier of using Euler's method in order to numerically solve the differential equations. And so that has already been done, and we'll just look at what are the effects of some of the parameters on the conversion and temperature. Okay, so for an adiabatic system, we have no heat in or out, but we have variation in temperature along the length of the reactor. And so from our energy balance, we have no accumulation. So what we're left with is and then our material balance is the design equation that we've used previously. Where we have that the change in conversion with volume is a function of the rate of the reaction, which is a function of both conversion and now temperature, because it's no longer isothermal, and rate constants depend on temperature. And then we have the inlet flow rate. And so what we need to do is solve those two things simultaneously in order to determine how the conversion and temperature are changing as a function of the volume or length of the reactor. So again, you can do this, I think I mentioned previously that you can do this, Vogler goes through a numerical method that doesn't involve numerically solving the differential equations. What he does is he sets up a table, and you set a conversion, then you calculate a temperature at that conversion. Once I have both a conversion and temperature, I can calculate a rate, right? And then from FA naught over RA, what can we do with that? Put a sign there. So what does that give us? Yeah, and that's sort of thinking about the Euler method. What this one specifically within Vogler is setting up, though, is actually the Levenspiel plot. So you get this, and this is what you have in your Levenspiel plot. Right? So you guys can see that you're going to get some value here, which is some point on this Levenspiel plot. And then you just keep going, and you can make the Levenspiel plot without solving this differential equation, right? Now that's not how we're actually going to mostly do things, but it does give context to where does, partly the Levenspiel plot come from and stuff, because there were times, a lot of reasons you guys might wonder, like, what is up with all these graphical solutions to chemical engineering problems? Like, this isn't the only one, right? You have McKay-Keeley, and there's others. Well, computers weren't so hot 20 years ago, so they feel like it's important to still teach you these basics, which are going to be used for mostly conceptual reasons, but still offer valid solutions for problems. So we'll do an example, and again, I'm going to set up the example. Yeah?
So how would this show up like on an exam that we can use numerical methods?
It would. I can't ask you to use numerical methods. I could ask you to make a Levenspiel plot with 7 data points, and you could go through that process, yeah. But I probably wouldn't. You know, on exams, what we're going to focus on are conceptual problems. So if I show you a temperature profile for a reactor, can you tell me whether it's adiabatic? Can you tell me if it's exothermic? Can you tell me if it's reversible or irreversible? Those are all conceptual problems I can ask you without asking you to actually make that plot. Making the plot requires a computer you don't have. I can ask you to set up problems, you know, to the point of solving, but not solving the differential equations, but writing them all out. And of course, I can ask you questions concerning CSTRs, because there we don't have differential equations. Okay, so as we go through this example, it's actually an example that we've already done for a CSTR. So we're going to now do it for a PFR. And then towards the end, I'll pull up a spreadsheet so that we can just look at how does the temperature change along the bed of the reactor, how does the conversion change along the bed of the reactor, how would those things change if it were exothermic versus endothermic, and all those sorts of things that we can play with. And I'll be sending out homework later today. And a lot of the homework, I'd say about half the homework you can do without a computer, and the other half you need to do the same procedure that we did in Excel to set up the Euler method in order to solve the differential equations, and then you can do that half.
There was no homework assigned this week, right?
No, it'll be due next Tuesday, and then you'll have another one due the Thursday after that Tuesday, but not 2 days after. 9 days after? Does that make sense? And then the exam. So you'll have 2 more homeworks before the next exam. All right, so an example, again, it's one where we've done it before, but we did it with a CSTR instead of a PFR. So some of this was just directly given in the problem, but some of it we kind of worked out. But anyways, it's a stoichiometric feed. It's A plus B goes to C. And the initial flow rate of both species, since again it's stoichiometric, is 0.2 moles per second. The inlet temperature is 300 Kelvin. It's an adiabatic reactor. It's liquid phase. Irreversible. And we need 85% conversion, and it's asking what volume of a PFR do we need in order to get that 85% conversion. Some other information. The heat capacity of each species. So I'm just going to make a little table of information given. So the stoichiometric coefficients are -1, and 1. The heat capacity of each species, temperature independent heat capacity, is 15 joules, or I think it's actually cal per mole Kelvin. 15 for B and 30 for C. Thetas, again, it's a stoichiometric feed, so 1, 1, and 0. And then we were also given some standard state molar enthalpy, and that was kcal per mole, -20 kcal per mole. This one was -15. This one was I believe 41. Yes. I think that's all the information. No, we were also given, never mind. The rate constant at 300 Kelvin is equal to 10 to the negative 2, and that's liters per mole second. And the activation energy, 10 kcal per mole. I believe that covers all the information that we were given. And like I said, we've gone through the same